We will start now with the first talk of the final day of our workshop. For this first talk, Thomas Oberlin is joining us live from Toulouse. Okay, thank you very much, Thomas, for being here with us. It is a pleasure to have you here, and thank you for delivering this talk. I will say a few words about Thomas' career. Okay, Thomas Oberlin holds a PhD in applied mathematics from the University of Grenoble. In 2014, he was a postdoctoral fellow in signal processing and medical imaging at INRIA Rennes before joining as an assistant professor at the INP Toulouse and also the IRIT laboratory at University of Toulouse. Since 2019, he is an associate professor of image processing and machine learning at Supero and member of the AI Institute ANITI. His research interests include hyperspectral and spectral imaging, latent factor models, data-driven regularization of inverse problems, and time frequency representations. Thank you very much, Thomas, for being here with us, and you can share your screen and start your presentation. Thank you.
Thanks a lot, Marcelo. Thanks for the organization and the invitation. So we'll share the screen. Okay. You see the slides? Yeah. I guess it's okay. Otherwise, please interrupt me. So the subject is inverse problems or image reconstruction problems, ill-posed estimation problems with generative neural networks. This is joint work with some colleagues here from different institutes, all at Université de Toulouse. Okay, the outline is the following. I will first introduce the problem, the background, then talk a bit briefly about two very different lines of works that tackle inverse problems with deep neural networks. And then I will explain the method we used and we propose, give some numerical experiments, and conclude with some perspectives. So what problem I consider here is inverse problems that are defined by some degradation operators. So here's the notation. We are given an image Y, or it can be a signal too, of course, which is a deterministic degradation of some ground truth X star, with A being the degradation operator, which is assumed to be known here. And of course, there is some noise. Here it's supposed to be additive. And how to estimate the X given Y is called the inverse problem. And a lot of formulations use the so-called variational formulation, where we try to optimize two terms, a data fitting term. So we try to find an X that fits the data well, given the model. But in general, there are infinitely many solutions, or at least the problem is ill-posed because A is badly conditioned. So in the general case, we need some regularization with some penalty function phi. And lambda is a parameter that tunes the strength of the regularization. So this is really a general setting which is used in a huge amount of problems. In many communities. It can be medical imaging, satellite imaging, signal processing, audio signal processing, and so on. I will give some simple examples. So this encompasses denoising in the case where A is just an identity matrix. It can be in painting where when A is just a mask, or deblurring where A is a convolution. Tomography, when A computes radial projections. But it includes also compressed sensing, where A is a random matrix, for instance, super resolution, pan sharpening, or even nonlinear inverse problems, such as dequantization, phase retrieval, and so on. And when solving this kind of problems, the critical part is the regularization. Okay, so there is a huge literature in signal and image processing dedicated to finding good regularizers for some given images or signals. In the last 2 decades, there have been a lot of work on sparsity, with, for instance, L0 norm, L0 quasi-norm, L1 norm, greedy algorithms, and so on. Of course, in many cases, the signal or the image we are looking for is not sparse, but we can find a domain in which it becomes sparse. It can be wavelets or finite differences. In that case, we have total variation. We can have also some row-rank priors, such as the nuclear norm, or group sparsity, such as the L12, such as what is enforced by the L12 norm. In that case, it's called the group lasso. And there is also a Bayesian interpretation of all this. If we assume that the solution satisfies, if we assume the probability density function of the X to be known, then we can use it as a prior in a Bayesian estimator that can be the MMSE or the map. So there is a relation between the variational side and the Bayesian way. All those priors regularizations are fixed, but we can also try to learn them given some data sets. A lot of work has been done in this way with dictionary learning since about 15 years. And in the last few years, people try to do the same with neural networks. So my talk is about how can we build efficient regularizations, data-driven ones, with neural networks. Before going further in the talk, I will just give you 2 examples of imaging problems we worked on in the team here in Toulouse. The first one is a problem in spectroimagery, in microscopy. I don't know if you know the modality EELS. It stands for electron energy loss spectroscopy. So these are spectrum images. Each pixel is a whole spectrum, like this one. Okay. So the shape is a bit weird. It's decreasing, and there are some thresholds here that carry most of the information related to the electronic structure of the material. So for the physicians, those thresholds are very important to characterize and to estimate. And the work here was about trying to have fast acquisitions of such spectrum images with kind of in-painting, but for hyperspectral, for spectrum images. So we proposed some hyperspectral in-painting algorithms that, given a few acquisitions here, reconstructed all the spectrum images by using standard regularizations, namely low-rank prior in the spectral dimension and something like total variation in the spatial dimension. Another problem in spectral imaging is the problem of combining multispectral and spectroscopy, multispectral image and spectroscopy or hyperspectral image. So this is a work we conducted with 2 colleagues in Toulouse for the 2 instruments of the James Webb Space Telescope. This is a simulation that explains well what we wanted to do. What we would like to do is to recover a scene, an astrophysical scene, at high spectral and spatial resolution. So this is an image, but remember each pixel is a whole spectrum like this. But we can't sense that thing because of instrumental and many other problems. What we have basically is a pair of images, one image with a few channels. The instrument is called NIRCam. So it has up to 20 channels, 20 images with high spatial resolution. And in parallel, we observe the same scene with a few pixels, but each pixel is of very high spectral resolution. And the goal of the work was to fuse those two data so as to recover a high spatial and spectral resolution image. So this is typically an inverse problem where we have two data fitting terms and we need some strong regularizations because the problem is very ill-posed. We did that with standard techniques such as total variation, sparsity, low nuclear norm, and so on. But we intend to use more recent tools such as neural networks in the future. Okay, so how can we use neural networks for helping to solve such problems? I will really make the distinction between many methods that try to invert to learn directly the inversion. Okay, so given y, we learn a network that will produce something as close as x as possible. Okay, so x, remember, y is the image the degraded image, and x is the estimation that you want noise-free and sharp and as close as the ground truth as possible. Okay, so those approaches learn to invert the degradation. They can work very well. They use standard tools of neural networks, deep networks, many parameters, stochastic gradient descent, and so on. All the recipe of deep learning. But they can have very high performance, but they suffer some limitation. The first one is that they need pairs. They need pairs of clean and degraded image to train the network because okay. And in practice, often those pairs are created with simulations. So because in practice we don't have those pairs, we sense y and, and we need to estimate x, and we don't have x. Another limitation is that all deep learning techniques, the methods lack stability, robustness, explainability too. So it's kind of black box. It's hard to interpret. And they don't make explicit use of the model of the degradation model A. Whereas in many situations, we know A with very high precision because of the physics of the instrument and so on. And it's better to use it directly instead of trying to approximate it through a neural network. And the last limitation is that it's not generic in the sense that if the model change or if the noise change, we need to retrain the network. Okay, the network is model dependent. And in practice, in many modalities, the model changes a lot because of the temperature, of the sensor, of the noise, of many physical causes. So I won't be exhaustive here. I just give you two famous examples of such networks that achieved very high performance. The first one is SRCNN to do single image super resolution. So it's a CNN, a convolutional neural network, quite standard, and it works quite well, and it has been improved by, for instance, this one, very deep super resolution, which is deeper and uses residual learning. And there have been a lot of models proposed since, such as USRGAN or many other models that are very deep, that work very well, that depend on the model and that rely on pairs of images to be trained. The other way of using neural networks is instead of learning to invert the model, just learning the prior, the regularizer. Okay, so we learn only the prior or the regularization on a data set only composed of clean images, x, y. There is no y here, only x's. And in the second step, we use it in a model-based inversion. Okay, using the operator A we assume to be no. This was called plug and play. And the first approach used BM3D, which is a deterministic denoiser. It was 10 years ago. And more recently, there have been a lot of works that use denoising neural networks. It's still called plug and play, okay? Because you plug the denoising neural network in a proximal gradient scheme to replace the regularizer, basically. Because the denoiser is similar to a proximal operator. Okay, the method I will consider here is quite different. It's close to this one introduced in 2017 by Bora and colleagues that use generative models. Okay, I will explain it afterwards. So the benefit of this plug and play of these two-step approaches is that we can have a well-posed formulation. We will see that this one is similar to a maximum a posteriori estimation, so it's something we know well. The regularization can be tunable with a simple parameter. It's generic because once you learn the prior, you can use it for any inverse problem. And of course, there are some drawbacks too. The performance can be lower, depends on the case, but the network is not specialized in a given problem, so it can be outperformed by a more specialized network. And another issue here was that the model does not generalize well. Okay, if you take an image that is quite far from the dataset, the method can be very bad. And this is something we worked and we tried to improve, and I will explain how. Okay, but before explaining the approach, I will just let me just check the time. Okay, I will just give a few words about neural networks and in particular autoencoders and generative models. So I don't know if you're familiar with them. A generative model is the latent factor model, okay, that can be written like this. You sample a latent variable, z, that follows a simple distribution, such as a normal distribution. And then you learn a model parameterized by theta, such as your data fits follows this distribution. Okay. We can assume that this distribution is some Gaussian centered on d theta of z, and d theta is the decoder network, is a neural network. Okay, so we can parameterize p theta by a neural network somehow. And although the model is simple, its inference is complicated. In most of the case, we try to optimize the likelihood, the marginal likelihood. Okay, marginal because we integrate over z, the latent variable. And unfortunately, for most models, such as most standard neural networks, this is intractable. You can't optimize that with gradient descent or anything. You need to do complex inference, such as variational inference. So variational inference is a very powerful technique that allows to not to optimize that thing, but a lower bound that is written here. I won't detail the equation here, but this is the lower bound we optimize, which is termed elbow. And actually, it can be seen as instead of optimizing this, optimizing under a restricted family of distributions that is called Q, that is called the variational distribution. And in practice, we often use normal distributions. Okay. So at the end, if we can rewrite the elbow as something like that. So this is the deep learning, no, the variational inference way of notation, but you can see this as a reconstruction error. Okay, so you try to, okay, this is the likelihood somehow. And this is a regularization. It forces the variational distribution that you use to be close to the P of Z, the prior somehow, that was imposed at the beginning. Okay. So at the end, you can train such models by minimizing two terms, a reconstruction error that can be something like MSE, and a regularization that in that case is the callback library distance between both distributions. Okay. And if you reparameterize the variational distribution by a neural network, then you end up with what is called a variational autoencoder. Okay. So maybe this figure that has been proposed by here is clearer. A VAE, so for variational autoencoder, is just an autoencoder, so a neural network that will have an encoder part that, given the image, will produce a mean and a vector of standard deviation. That if you sample from that, you end up with a latent variable, which is stochastic. And if you go through the decoder, then you reconstruct an image which is supposed to be close to that. Okay. So this is a way to approximate the problem, the inference that is intractable with variational inference. Another family of generative model I will talk about is called invertible neural networks. Sometimes it's also called normalizing flows. So the idea is the same. We have the same model, okay, but instead of using variational inference, we use a very specific decoder so that the likelihood is tractable, can be optimized exactly with gradient descent. And I won't detail all the recipe, but the main tools are that we need bijective invertible layers in the network. So this prevents from using any convolution. So there are very specific layers called ACT-norm, and okay, I won't detail that. And the other recipe is that, okay, if we are invertible, we can optimize the likelihood, but we need to do it efficiently because we are in the dimension is very huge, as with all neural networks. So most of the models, most of the layers have triangular Jacobians, so that the determinant can be computed easily. And so the gradients can be computed easily and backpropagated. Okay, so to summarize, those networks are quite simple compared to CNNs, for instance. So in order to be powerful, we need a lot of layers, a lot of steps of flow. That is the equivalent of the layers. Okay. I will just give you an example of such a network. This is called GLOW. It was introduced in 2019 in that paper. So it's an invertible neural network that use, okay, those layers. I won't detail them. So they allow you to sample. This is an illustration where the network was trained on celeb A, on a data set of faces. So once you have the once you learn the model, you can sample from it. So you can create fake faces. You all see those. It has been quite popular a few years ago. But you can also do a lot of things, such as interpolation in the latent space. So this is an illustration where you have two real faces here. You compute the latent representation, the Z, corresponding to that one and that image. And if you interpolate linearly in the latent space and you generate again all the in-between Z's, then you have a very nice morphing between both images. Okay, so you can, if the latent space is well structured, then you can really do a lot of things. Okay, it's not what we will do here. We will use such a model as a prior for regularizing an inverse problem. Okay, so I will explain the proposal of this seminal paper from Bora and colleagues. So remember, it's a two-step thing. You first learn a generative model, and once it's learned, the weights are fixed, and you just optimize an image at the end in the second step. So you don't optimize the weights anymore. This is fixed, okay? And the second step is just given the degraded image, find the Z that best fits the data. So remember, before we had AX, and X is D of Z. So it's very similar to the formulation before, except that instead of optimizing on X, we optimize on Z. And at the end, if we apply again the decoder, then you have the X, the estimate at X. Okay. And in that paper, they propose to add this second term, which can be seen as a negative minus log P of Z, because Z was assumed to be normal. Okay, that's why you have a least squares term here. Okay, so this can be seen as the maximum a posteriori estimator in the latent space, because you optimize on Z, not on X. And it can be very powerful, but it's very sensitive to any mismatch in the prior, in the P of Z. So it cannot generalize well to unseen, to different images. Another way to see that limitation is that the solution belongs to the range of the generator, to the range of the function D. Okay, this is obvious here. And if that range does not correspond to the image you want to reconstruct, there is no way you can have a good estimation, even if the degradation is very little. Okay, so what we proposed with an intern 2 years ago is just to optimize directly on X. Okay, so replace D of Z by X, and you end up with something like this. Instead of X, you have the encoder of X, which is the same thing in the latent space. So instead of using the decoder, we use the encoder, and we optimize on X. Okay, but this is very similar to this formula. And if we also want to use the fact that we hope to find an image that is close to the range of the generator, T, we can add a term like this one. Okay, this is a relaxation. This is not a hard constraint. Okay, you can have some error between the true image between the estimation and what is in output of the autoencoder. Okay, so we term this formulation analysis regularization because it's very similar to what was already done between analysis and synthesis with dictionaries or frames. This is not a map because we didn't put the Jacobian here, but we could do that. We could modify it to have a map in the image space. And we'll see that it generalizes slightly, really better in some cases. Okay, another thing we proposed is that actually most of the generative models assume a very simple prior in the latent space. So in all generative models with neural networks, P of Z is assumed to be Gaussian, unimodal Gaussian. And this is really a problem because mapping a very complex distribution, P of X, into P of Z, it's very hard. And in some way, if you want to do that, you need a very complex network that will have very high Lipschitz constant, for instance, that will be quite unstable. Okay. So a way to overcome this is to remove the constraint of generativity. Okay. So we try to use just an autoencoder or a regularized autoencoder where you just have a fixed regularization that is not generative. And then after the training, we try to estimate the distribution of the latent space, of the data set in the latent space. Okay. So this works quite better, but it's still ongoing work. So I won't present that now. I need to mention again, I'm not exhaustive, but there are many works in the last 2 years that tackles very similar problems, either on the variational side, for instance, this work from Gonzalez, Andres Almanza, and colleagues, where they try to do something in between the map in X and Z with alternate optimization. And there are also a lot of works in the fully Bayesian way with sampling techniques, MCMC, and so on. Because the generative models can be also used to sample a posterior. Okay, this is a review on the subject that includes dozens of references similar to all those works. Okay, so if you're interested, I suggest you to read that paper. Okay, now I will give you a few results. So starting with something which is a bit a toy example, but it's still highly used for all these techniques. So we used an experimental setting similar to that paper from ICML 2020. So we used 64 by 64 images of faces. We used the GLOW network I mentioned before with 32 steps of flow, 32 layers, and we tune the parameter lambda manually. Something which is very important is the initialization, because either for the analysis or synthesis formulations, we have a non-convex problem, so initialization matters. And a very simple but quite good strategy is to initialize at 0 in the latent space when we do the synthesis, or at d of 0, the image of 0 by the generator when we do the analysis formulation. Okay, somehow 0 is in the middle of everywhere because we assume a Gaussian prior. So this is, according to our tests, quite good and fair comparison. And we consider very simple inverse problems, simple formulations, but the problems can be hard because we remove a lot of information. So we consider in-painting either with a random mask or a structured mask, a squared of 10 by 10 pixels in the middle, deblurring, and super resolution with factors 2 and 4. And here are the results. Okay, so the first line is the ground truth. The second line is the observation, the degradation, which is a simulation here. And the two following lines are the solutions given by the synthesis, which was proposed by Bora and colleagues, and the analysis formulations. And what we see is that here for the deblurring, both techniques give a good result on the face, but the background is not well synthesized by the synthesis formulation. Okay, it's not well recovered. And this is because the background is a part which is out of distribution in the way that it has similar patterns have not been seen in the training dataset. So the network is not able to create something that is close to that patterns. Okay. At the opposite, in the analysis formulation, we optimize directly in the image space, so we don't have any problems to recover something which is very close to the good background. Okay, so this is exactly what I mentioned by the synthesis is more sensitive to out of distribution and mismatch in the prior. Okay, now if we look at a harder problem, which is super resolution. So super resolution is blur, then subsampling by a factor 2. So it's harder because there is a blur, and after the blur, there is subsampling, which removes a lot of information, high frequency information. And here we observe the same thing. Okay, the background is not well recovered, but if you look at the analysis, then we can see that the results is not good anymore because somehow the analysis formulation is less powerful. It contains less regularization because there is no the constraint to be on the image space of the generator. Okay. And we can see something very similar for the in-painting. So on the left, you have the random mask, which is the easier problem because the missing information is a bit everywhere, but you sample pixels everywhere, so it's easier to recover the faces. And here, again, the synthesis phase that recovering the background. And there are some artifacts on the faces, but okay, both methods are fair for the faces. Whereas on the right side, we clearly see differences. The analysis phase at recovering realistic faces, okay, because there is too much loss of information. Whereas the synthesis recovers realistic faces, but those faces are quite different from the ground truth. Okay. Again, we lost too much information, so there is no way we can recover exactly that face. But still, the synthesis method will give you a face because it optimizes in the latent space, then it applies a decoder, so it will produce something which is a face, which is similar to a face that has been seen in the dataset. Okay, so of course we conducted some more quantitative analysis, and we see something very similar. So for most problems, analysis is better, either in PDSNR or SSIM, except for in painting, where with structured mask, where the synthesis is better. Okay, so this is an average over 50 images from the test sets. Of course, those images have not been seen during the training of the generative model. And since we are quite interested on the out-of-distribution examples, we also made some toy experiments with really out-of-distribution examples, not only the backgrounds, but even the whole picture that is out of distribution. So this is an example with a cat. This image is of low quality, but we can still see the differences between synthesis and analysis. And we have the same thing, that is synthesis fails at producing something close to the image because there is no way that the generative model can produce a face of a cat. It has been trained on faces on humans and not cats. Whereas the analysis does not have this strong constraint, so it can still, when the problem is not too hard, which is the case with deblurring, we still have some information, even if we lost high frequencies. Then the prior on the that was learned on human faces is still correct, not perfect, but still correct to recover a cat face. Whereas the synthesis fails at recovering something close to a cat. Of course, when the problem is very difficult, such as here with in painting with the square mask, then both method fails because this one has not the correct prior, and this one has not a powerful enough prior somehow. Okay, so to summarize, I hope I convinced you that regularization with deep neural networks is something promising because it combines data-driven priors with a model-based inversion. So it's generic, well-grounded, can be a bit interpreted, even if we use a neural network that is still something a bit black box. And if you need to choose between synthesis and analysis, you may use synthesis when you have very little information about your data, your estimation X. But as soon as you have enough information, it's better to do analysis because then you will be less dependent on some bias or mismatch in the prior. And then I didn't show it here, but we found out that autoencoders, so non-generative models, can be used in the same way to regularize similar problems. Okay. Now the question we are facing now, and I will give a few words on that, is how to use such techniques for real applications, such as we are considering in Toulouse, because there is in Toulouse the French Space Agency. So we are working with them on how to adapt those techniques to satellite images. And the problem is that satellite images are far more complex than faces. Human faces are already very complex in terms of data, but they are still simple compared to satellite images. Okay, so there is no way we can learn a very good generative model of a satellite image, or we need billions of parameters, and we don't do. We don't want to do that. Okay, so to tackle more realistic applications, we really think that the generative model is maybe something that is too hard to find. So maybe autoencoders, non-generative autoencoders, should be enough. We also need the model to be covariant with translation. So fully convolutional autoencoders are good candidates for that. So we started to investigate a bit the issues with the data set provided by the French Space Agency, the CNES, that well simulates satellite Pleiad images that are optical, very high resolution images. The resolution is 50 centimeters. So the kind of model we use is those ones. So we have an autoencoder, which is fully convolutional. So the latent space is structured. We still have two dimensions, two spatial dimensions, and the dimensions of the channels. And the problem is that in that case, we need to use the structure. We cannot see the Z as something which is drawn IID because there are some spatial correlations and the feature maps, the different channels have different statistics. Okay, so we try to investigate that a bit. Yeah, we found out that most of the feature maps have Laplacian distributions that could be used with, for instance, a weighted L1 term on Z to regularize the problems. Okay, so we have some short-term objectives, tune the network, better parameterize the methods, and the perspectives. There are also some middle or long-term perspectives that will consist of use conditional generative models, because building a generative model of a complex scene such as a satellite image is complex, is maybe unachievable. But if you condition that on some raw resolution or some rough estimate of the image, maybe it becomes easier and feasible. We also need maybe some multi-scale models, such as hierarchical VAEs or units. And we also need to better model the statistics in the latent space in case we don't use a generative model. Okay, so that's it for me. And I will be glad to answer any of your questions if you have.
Thank you. Thank you very much, Thomas, for your interesting talk. Do you have any questions here? Me? You can. I have two questions, I should say. By the way. You hear me, Thomas?
Yeah.
I was just wondering, in the image you showed us when you have this image when you've got the background and the foreground, and you said that the background cannot be properly reconstructed. What about trying to have different priors and try to find analyze the image before you compute your parameters, trying to find what type of image you are dealing with, so that you improve the construction. So at two different priors for the background and for the image, for instance, for the face, or because usually people try to separate maybe the texture from the geometry in images. So it will happen in many other cases where you have different type of structures in an image. So if so maybe if it's not, maybe it's computationally difficult. I don't know.
Yeah, this is a very good question. Actually, yeah, you're right. In many cases, we know that somehow the statistical model of the image is a mixture. Okay, it can, because there are some geometric parts, some textures, and so on. We tried something based on this idea.
Again,
here. So I mentioned that we tried something with non-generative models. So we just have an autoencoder. We train it to reproduce the images. And at the end, we try to analyze the Z, the statistic of the Z. And actually, we tried with a Gaussian mixture model. So in that case, we hope that for if there are some classes in the data set, such Gaussian mixture models can capture the diversity. But then the initialization is harder because it's more non-convex than if you have a unimodal P of Z. But yeah, of course, it's a core problem.
Maybe you could see that when you compute your prior, right? Maybe you can compute the error you make at different location in the image, and you see that the prior doesn't correspond to, when you encode your image with your prior.
Yeah, but actually in the model we used here, it's they're not fully convolutional. So they see the whole image. So they cannot. There is no way they can separate the background and the face. Okay,
Yes,
it's really, they see the whole thing. With fully convolutional models, yes, you might segment the feature map, but yeah, it's okay. It could be a good idea, but of course it's hard to. Then you need to segment the image and to cause the right prior at the right place, and this is not very easy in practice. But yeah, of course it can be.
And I had another question that was regarding slide 17, I think. When you changed your minimization process, so you've got this one, and then you say that by changing it to slide 9, you had something which was more general. And why is it more general? Because in fact, you still have the decoder and coder, which is specific to one image, right?
Yeah, but of course it depends on the model. But if you have an autoencoder where the latent space is smaller, okay, then the dimension of Z is lower than the dimension of X. Okay.
Yes.
So basically, here you have a stronger regularization. You have more constraints on the solution than here. It's what I want. I meant.
You lose generality, but you gain computational time by encoding first in a small basis. Or
yeah, it can be more costly to do that. Yeah, you're right. But again, it depends on the model and on the dimensions of the latent space and the image space. Yeah, if you need dimension reduction, then it's better to do synthesis. But yeah.
Okay. And well, okay. Thank you. Thank you, Thomas.
More questions?
Hello, how are you? Thanks
Hi.
for your presentation. I work with speech enhancement algorithms, and many times when we apply some speech enhancement, we get a spectrogram of the speech signal that if we were too aggressive in the denoising, we get we get to eliminate most of the noise, but we lose a lot of information of the desired speech too. So we can see the spectrogram with a lot of gaps and holes. And so I was thinking that maybe your developments can be applied to some kind of post-processing to reconstruct the real spectrogram after you lose all this information. Especially, it's interesting that you show somewhere there that you have been working with Laplacian distribution, and the spectrograms tends to have a Laplacian distribution. So maybe it's an interesting point to work there. Have you ever tried something in that line?
Yeah, I didn't mention audio and spectrograms because it's harder than with images. Actually, I'm not aware of small and efficient generative models working on audio or spectrograms. There are some, but they're more complex, they are recurrent, and so on. And the other problem is related with the phase. Most of the time, we want to keep the phase, and in that case, it's really hard to build a model.
Yeah, but you can work with
model because
we can use the face, the noisy face, for example, or some enhancement on the face from other side. But you can just work with the amplitude or magnitude spectrum.
Okay, if you're only considering magnitudes, then I think, yeah, you can there are some many audio signal processing tasks are already performed with convolutional neural networks on the spectrograms. I'm not sure there are generative models for that, for synthesizing spectrograms. But yeah, it will be definitely something to to try. Yeah, I don't know well enough the literature on the subject.
Okay, thank you.
Any other question? We have one question from the virtual audience in YouTube. It was asked when you were showing this slide 17, and I think it was already answered. But anyway, he asked, did you implement this model on real person images? And yes, of course, you showed some examples after that. And right now he's asking, maybe I missed, what's the accuracy and the size of data?
The accuracy on the size?
The accuracy and the size of data. I think you showed the number of examples, and you showed performance figures.
Okay, so the performance can be very good here. Of course, it depends on the. As always with machine learning techniques, it can work very well if your image is very similar to what you saw in the training set. So it's hard to really say, answer that question, but the performance can be very high. And I didn't mention it, but in the paper of Bora, there is some theorem very similar to the ones in compressed sensing. You know, if you have a number of measurements on the same order of magnitudes at log of n, then you can recover perfectly or asymptotically perfectly the image. And with compressed sensing, the number, the quantity of interest is the number of non-zero coefficients, the sparseness index. And here's the size of the latent space, which is the counterpart. Okay. So yes, the method is very powerful, both the synthesis or analysis. But they are quite costly. So maybe the question on the size of the image was related to the computational complexity. I didn't mention it, but this optimization is performed with gradient descent through the network, okay? Because in both cases, you have E or D or both. So you have neural networks. So you need to do gradient descent. And it's costly, but you can do it on GPUs, so achievable. And here I used 64 by 64 images, but we made experiments with 200 or 300 by 300 images, and it's not a problem. You can, as always with deep learning, you cannot treat in one shot a huge image of size 5,000 by 5,000 pixels, but mainly because of memory issues, because it will require too much memory on your GPU.
Okay. Any other question here? Yes, Matthias.
Hello. I have a quick question. Have you thought of how would you translate this approach that you developed in video processing? Whether would you be repeating the exact same thing for every frame, or would you add something associated with the time evolution of things? So just a comment, if you can comment on that. Thank you.
Okay, of course you can apply frame by frame, the technique frame by frame, but it will not use the temporal information, so it will not be very efficient. Conversely, I'm not aware of generative models that can produce video sequences. Maybe there are, but I didn't look at that because I didn't consider video. But if there are, it would require very large models. So I'm not sure this is easy to transport that to the video processing, except maybe if you do frame by frame analysis with some additional constraints. For instance, if you constrain the latent variable to not to move too much from one frame to another one or something like that. Yeah, I don't know.
Yes, Thomas, he's happy with your answer. Thank you. We're having just some technical problems here, Thomas, but no, don't worry. We're still listening to you, and you can hear us, right?
Yeah.
Okay. Yes. Any other question? No. So if we do not have more questions, then we can thank Thomas again.
Thank you.
Thank you very much, Thomas, for your talk. It was great to have you here with us, and we look forward maybe to be with you in our next event. Okay?
Yeah, I hope so.
Thank you very much.
Thanks a lot. Bye-bye.
Bye-bye.